Sound check, testing 1, 2, 3, sound check. All right, we're going to give this a few more minutes before we get started. We still have some people joining. You are in the right place, but we will get started in a few minutes. Hello, everybody. I know it is just on the hour, but it usually takes everybody a couple minutes to log in and get sorted. So we're going to give everyone a few more minutes before we get started. All right, we'll give it one more minute. I still see there's a few dozen people trying to join, and then we will get started with today's webinar.
Okay. Well, good afternoon, everybody, and welcome to Hydro International's Stormwater BMPs Design Do's and Don'ts. What's going on? Already a technical difficulty. All right. Okay, let's start over. Okay, good afternoon, everybody. Welcome to Hydro International's webinar, Stormwater BMPs Design Do's and Don'ts. My name is Mark Johnston. I am the American Stormwater Senior Project Engineer, and myself, along with 4 other technical support team members, are here to answer your technical questions regarding any of our stormwater products. Our Senior Project Engineer is John Larson, and we have 2 project engineers, Griffin Wood and Eric Robinson. Anytime you contact Hydro for technical support, you're just as likely as to talk to any one of these individuals. And we do encourage reaching out and talking to us directly. It's the easiest way for us to understand a problem and get you a solution in the time frame that you need. Today's webinar is, we're going to cover a little bit about Hydro International. We're going to stress our sizing tools, where to find them, and the benefit to you to use them and become familiar with the resources that are on our website. We're going to discuss choosing a product, how to configure a project in your storm drainage system. That will entail a discussion about online versus offline structures. Some general considerations when designing separators and filters. A very important topic that we don't hear discussed frequently, but it's extremely important, is design with maintenance in mind. You know, where are you going to locate these? What kind of access do you need? And finally, we're going to close with our recommendations about writing a specification that clearly calls out the objectives and makes it easier for the various vendors of BMPs to propose something that meets the project specification. And finally, we're going to close with a brief survey and a chance to win a Amazon gift card. As our name implies, Hydro is truly international. Today I'm presenting from our Stormwater division in Portland, Maine. We've been here for over 20 years, but as you can see from the map, we have offices worldwide. And along with the offices, the Hydro offices, we use an extensive network of product representatives that are available for pricing and assistance as well. Okay. Because we are worldwide and we are involved such an extensive range of topics, wastewater, stormwater, CSO, industrial water treatment, we have a wide range of capabilities and a lot of internal resources to pull from. So those resources are a great resource for you as well. It's just a matter of reaching out and asking the right questions. We have in the North American office where I'm presenting from, we do have a world-class laboratory that we utilize for product development as well as testing to ensure that we comply with various test protocols established by agencies all across the country and Canada. In order to get the approvals, we collaborate with a lot of universities. They help us hydraulically characterize our products. It's a truly independent third-party testing, and it's an integral part of doing business in the United States. Approvals. Everybody has their own test protocol, their own treatment objectives. These are the people that we worked with to get on approved products lists. A major part in choosing a separator is making sure that something's on an approved product list. So these are some of the web pages that you can go to see if Hydro's products are on the list. All right, so moving into our product sizing. That last web page and this web page are pointing out where to access the sizing tools on our website. This particular one, you can access the tools, all the tools for all our products. In addition to that, you can get drawings, specifications, sizing summaries. So it's a good spot to get familiar with on our website. Selecting a stormwater BMP. So at some point, when you're going to select a product to treat your stormwater runoff, you have to determine what you want to treat, what you want to remove, and how much flow do you want to treat. So a good starting point is to, the standard target pollutant for stormwater tends to be solids, TSS. Some places have a trash specification. Some areas are more particular. They may be looking at nutrients. But as a starting point, if you look at the size of the solid you're trying to capture, you can, from there, decide which of our products you want to use. On the right-hand side, we have the Hydro Dry Screen, and that's for capturing gross solids, leaf litter, cans, bottles, trash, and coarse solids, the heavier grits found in storm drainage systems. They're good if you're after like 80% TSS in the fine to coarse solid range. Then you'd want to utilize a separator, hydrodynamic vortex separator, either the First Defense high capacity, which is middle left, and next to that, to the right of that, is the Downstream Defender. And if you're in an area that requires advanced stormwater treatment, that maybe they're looking for nutrients or they have more stringent regulations, you'd probably want to consider using a hydro upflow filter. That device can capture much finer particles and the pollutants associated with those finer particles. Okay, as I indicated previously, the first place you're probably going to start is with your stormwater manual. The local regulations are going to define what you need to treat and what pollutants you need to remove. Regulations and specification are getting much better, but in the early days, we used to get paragraphs in stormwater BMP manuals that would have a mixture of sizing methodologies, and some of them are mutually exclusive. Like on the one hand, they define a water quality storm and define a certain percent removal of TSS, and then on the other hand, in the same paragraph, they would say a net annual calculation is acceptable. The problem with the net annual calculation is it frequently ignores the fact that you need to treat the peak storm flow. Well, I'm not going to cover that in depth in this webinar. We do have other webinars in the series that discuss alternate sizing methodologies. But hopefully you have a well-written BMP. It clearly defines what the target pollutants are and how much flow you need to treat. And as I alluded to earlier, it's good to check if there are approved products lists, either in the BMP manual or on the various regulatory website pages. And finally, just as an overview, your treatment objectives will guide your product selection. Fine particles, think filter. Very coarse treatment, high flow rates, think the hydro-dry screen. And then, of course, the typical treatment devices for 80% TSS removal will be one of the two hydrodynamic vortex separators, the First Defense or the Downstream Defender. And again, you know, the online sizing tool is there. It's a good place to start, and you can always call us if you have additional questions. Okay, there are other considerations to take into account when you're choosing a BMP. For example, are there any hydraulic concerns on the site? Do you have a tailwater condition? Is the storm drainage system flat or shallow? I mean, how is head loss going to affect the system? Anytime we prepare a submittal, we always check upstream water levels. We're vitally interested in making sure that our devices don't cause any problems in your storm drainage system. So we do check head losses, and we do check for the presence of tailwater conditions to gauge how they may impact the design. Okay, so once you choose a system, depending on your peak flow rate, you have to decide if you want to place it online or offline. And we're going to get some. We're just about to get into some examples of the online versus offline, but basically, you could size a system that meets your treatment objectives. Say you had a 5-acre site, and you only needed to treat a small portion of it. Say you had 1 CFS that you needed to treat. You could size a small separator to treat that. But the problem would be that the 5 acres is generating too much runoff, and the pipe's too big for, say, a 4-foot downstream defender. So your choices are to either upsize the treatment unit, use an internally bypassed treatment unit, or design a system offline. An offline system typically involves a diversion structure of some sort and an internal weir that will bypass flows beyond the water quality flow rate. So in these examples here, the top layout is just an upstream junction structure with 3 inlet pipes and all the flows passing to a downstream defender in this case. It's not internally bypassed. Everything that goes to the separator is treated to some degree. You know, we size the separator to treat the water quality flow at 80%, but once you go beyond that, then your treatment efficiency starts to drop. The key point to remember here is you don't want to pass so much flow through that you're causing a flooding issue upstream, or that you're risking washout of previously captured material. So what we're going to do is make sure it's sized for the water quality flow, and then check the peak flow. And then if the peak flow is excessively high, we would recommend an offline arrangement. Offline arrangements typically are less expensive than upsizing to the next size separator. The bottom layout is an example of a single structure diversion where we set the weir to divert water quality flow, And then once that's treated, higher flows pass over the weir untreated. And the final example of a bypass arrangement is a two-chamber bypass. We have a weir structure upstream that diverts the water quality flow. And then downstream, we have a junction structure where the treated flow gets tied back into the main line. There are other types of configurations. Each has its different hydraulic checks that we need to make. You can have two separate outfalls. There are many different ways of laying out a bypass. Okay, maintenance considerations. Access is the key. We need to make sure that we can get a truck, if not right next to the separator, somewhere nearby. We need to make sure that the castings do not impede access with either the Vector truck or other devices that are being used to remove the floatables, the solids. Many of the separators can accommodate a wide range of castings, but they need to be modular enough so that you can disassemble them to have full access to the sediment storage sump and the floatable storage area. Depth is a major consideration. If you have a storm drainage system, say that's deeper than 25 feet, you might find that the local Vector truck can't pump that deep. We know there are trucks out there that can, but that's something that the local municipal service may have to contract out, or they may have to use other means, trash pumps, something to get the sumps clean. If a system's too shallow, the flat top can be really close to the internal components, and that can limit access as well. There's another consideration with the shallow systems that will concerning head loss and fitting the internal components into the manhole that we'll get to shortly. And the final but most important consideration is safety. It's not always possible, we understand, but we like to keep them out of roadways if we can. Avoid major traffic disruptions. It's not good to have people popping out of manholes in traffic, that sort of thing. So access, castings, depth, and safety, very important things to consider when you're making sure that you can maintain these devices properly. A few examples. We do see a lot of separators installed inside buildings, parking garages. Sometimes they're buried in the floor, and sometimes they're freestanding. That's okay, but you need to make sure that the equipment that's going to be used can access it. So this is an example of a downstream defender placed in the floor of a parking garage. And I'm not quite sure if that Vector truck will be able to clean it out or not. I suspect it will be able to, but vertical clearance is an issue. Yes, this particular unit's in the middle of a courtyard. There's no road access to it, so you can see that the clean-out company had to manhandle their pipes, get them to the separator. A lot of labor, probably a lot more time to accomplish the clean-out, so higher costs. And again, the site dictates that it has to be in a difficult place to reach. But if that can be avoided, that's a good thing to do. Here's the safety aspect. They could drive a truck close to the guardrails, pump it out, fine. But when it's time to actually change the filter media, you're going to have to get somebody in the manhole. Our separators typically don't require confined space entry. But if it's off the pavement and you can set up your equipment and not have to worry about traffic, that's a good thing. Okay, tips for designing hydros products. We're going to briefly go through each product and discuss some special considerations for each of them that we take into account when we're putting together submittals and proposals. Okay, First Defense Hydrodynamic Separator. We have multiple models to treat various ranges of flow rates and store various amounts of pollutants. It captures fine to gross solids. It's got an internal bypass. This is the inlet side, the inlet chute. Flow comes in, head builds up on the inlet chute created by this weir, and then then the low flow or the water quality flow goes into this treatment volume, swirls around, solids settle out, and then it comes back up through the outlet chute and out through the pipe. Internal weir generates the head on the inlet chute, and high flows bypass or pass over the top of that weir. It's one of the standard go-to separators that we use to capture 80% TSS. Because it has an internal bypass and can accommodate a wide range of pipe sizes and flows, it's normally placed on line. Again, it can accommodate a wide range of flows and peak pipe sizes. It's not unlimited, so when you are designing one of these into the system, you need to pay attention to the numbers of pipes you have and their orientation. We have to make sure we miss the weir, that we get the pipes in the upstream side of the weir. All right, moving on. Okay, and again, this one's internally bypassed. And again, as with any products, if it's approved in your area, it's good to go, good to use. If it's not, it doesn't mean that we can't propose it, but it may take a little work to get the regulator on board with using the product. Okay, I already discussed this, just checking the product literature to get an idea what the water quality, peak flow rates, pipe sizes that each unit can accommodate. Again, surface inlets, you can put just about any inlet on top of this, but again, we have to have full access to those critical areas. The sediment access sump, the sediment shaft, and then both the inlet and the outlet chute to remove any debris that may have gotten stuck in that area. All right, so this is a situation where a shallow system can be problematic. So we have minimum rim to outlet invert clearance requirements. What we don't want is a situation where we have to trim the internals down so much that the underside of the concrete lid is very close to the weir. So we don't want the systems to become a restriction. Now we can trim these down quite a bit, but we have to check the upstream hydraulics. We got to make sure that we can get the flow over the weir without causing any flooding issues or any other type of hydraulic issues. It's best if any stormwater treatment system is not used as a drop structure. Now, these devices can accommodate small drops, 2-3 feet. And depending on the orientation of the pipe and size of the pipe, they can accommodate some large drops. For example, say you have a 6-inch pipe coming in, not a very high flow rate, and you need to come in 10 feet higher than the invert out. That's okay if it's not pointing directly over the weir. We don't want the flow cascading over the top of the weir untreated. So if you can orientate the pipe so that's running crossways to the weir, not really perpendicular because there's an angle between those two weir walls, but just be careful. The point I'm trying to make is just be careful with drops. They can accommodate some drop, but they shouldn't be relied on as a drop structure. In general, it's not good to use any treatment device as a drop structure. Okay. All right, as I discussed earlier, this device has an internal flow control, the weir. It's an internally bypassed device. So that drop chute on the inlet pipe side requires a certain amount of head on it to divert flow into the treatment chamber. So if you're discharging to a downstream water body, a lake, a ditch, a pond, anything that has a water level that could affect that weir or submerge that weir at the separator, then it's going to reduce the treatment flow rate through the device. It's going to tend to want to bypass over the top of the weir rather than going down through the drop chute and through the treatment chamber. So that's something that with internally bypassed devices, you need to take more consideration with downstream tailwater conditions. Moving on to a downstream defender, this is another device that you'd choose to capture 80% TSS. This is another typical go-to treatment device. It does not have an internally bypassed. It is not an internally bypassed system. So anything that goes through it gets treated to some degree. We size them to treat the water quality flow, and then we check the system design flow, the 10-year, 25-year flow, to make sure that it's not causing any hydraulic issues upstream. It's not a hard and fast rule. If you've got a really deep system and you want to pass, the typical capacity of an 8-footer is 15 CFS, an 8-foot downstream defender. If you wanted to pass 17 CFS during the 100-year storm and you had enough freeboard in your system, that would be acceptable. It's a very infrequent event. You've got enough freeboard, it's not causing any flooding. We're not concerned about the internals getting damaged. So that's acceptable. So it's another situation where if your design parameters don't meet the product literature, it would be a good idea to reach out and contact tech support. And finally, same idea, is an approved products list in your area. Makes it easy to choose any type of treatment device if you got local approval. Okay, same with other products. Our internal components take up a certain amount of space, so we need to make sure that we have enough room between invert and underside of the lid to accommodate those internal components. So if you have very shallow systems, it's something to bear in mind when you're laying these systems out. All right, a very common mistake with the downstream defender is, where do you place the outlet? As you can see from this diagram, the inlet comes in below the outlet, but where you place the outlet is very important. What we like to do is place the outlet on the hydraulic profile. So what that means is we want to make sure that the outlet is not above any of the inverts into the upstream structure. We're going to get to some diagrams shortly that show that. But the way I like to explain it is, for now, let's start at an upstream junction manhole and assume there's a pipe going. No, wait a second. I'll wait until we get to those diagrams before I get into that type of discussion. Okay, so we set the outlet on the hydraulic profile, and then we submerged the inlet pipe, one inlet pipe diameter. So say we're setting the outlet on 100, elevation 100, and we wanted to use a 12-inch inlet pipe. It's a 6-foot diameter downstream defender. We'd set the inlet at elevation 99.0, 1 foot below the outlet elevation. And the final check that we would make would be the peak flow. If the peak flow grossly exceeds our recommended hydraulic capacity, we could either upsize the unit, recommend upsizing the unit, or propose an externally bypassed layout. So here's a downstream defender in operation. If you look at the outlet pipe, you can see there's flow in the outlet pipe, and if you look at the pipe going into the upstream structure, there's also flow. So the way this should be laid out is that after a storm event, the DD is going to drain down to its invert out. That pipe into the upstream structure should drain down as well. So if the DD outlet is placed lower than that pipe into the upstream structure, then that's correct placement on the hydraulic profile. There's always going to be some standing water on the inlet, in the inlet pipe, which is normal, but what we really want is to make sure that storm drainage network upstream of the defender drains completely after a storm event. And here's a schematic representation of that. This is a situation that's very undesirable. Say we have an outlet control structure upstream, and they're using some kind of control to store water in that 48-inch pipe. The invert of that 48-inch pipe is at 100, and so engineers design storm drainage systems like they always do. They run their outlet pipe at, say, 1% or 0.5%. And then once they get to the defender, all of a sudden the outlet pops up, the outlet pipe diameter. So in this case, the outlet's at 101.5. The inlet's in the upstream structure is at 100. So the defender outlet's holding back 1.5 feet of water. So that's 1.5 feet of dead storage. We don't want that situation unless it's intentional. Sometimes it is, but normally it's done by mistake. So anytime we see a set of plans, and we think it was a mistake, we'll bring it to the engineer's attention. So this is not the correct way to design a defender in, and it's not that the defender won't work properly. It will work properly. It's just the fact that the device is holding back more water than it has to. Here's an example of correct placement in the storm drainage system. We've got the pipe going into the control structure at 100. I'm going to look right at the DD outlet now and ignore the pipe in between, and the DD outlet's at 99.9. So it's lower than that pipe going in. And then I submerge the inlet pipe, one inlet pipe diameter, 12 inches to 98.9. So the only place that's going to have some standing water is, about half the inlet pipe near the separator. All the pipes upstream are going to drain completely after a storm event. Okay, moving on to the dry screen. As we talked about earlier, this is captures gross solids, TSS, leaf litter, trash, can accommodate large pipes, large flow rates, and it captures the coarser sediments. This is another device where you should take the tailwater into consideration. A lot of times these are placed near water bodies, and it's fairly tolerant to a tailwater condition. But if most of the time the tailwater was like near the top of this wall, we would probably either have to upsize the system. That would be the only. We'd have to recommend upsizing the system in order to get treatment. We need to have a significant portion of that wall above the downstream tailwater to get to screen the water quality event. It's a large. These tend to be, large structures. You're going to have somebody get in them, I believe, depending on how dirty they are. If they've captured a lot of gross solids, you'll probably have to get somebody in there to remove the screens and remove the debris. So maintenance access, as with all the structures, is another important consideration. Okay, the Upflow filter. As we touched on some of the earlier screens, this is a device that you'd use to capture very fine particulates and the associated pollutants. A lot of regulations, I wouldn't say a lot, but we've seen a trend of treatment objectives where people want to capture finer and finer particles. So if you have a environmentally sensitive area and they like to capture finer particles, this is the type of device that you'd use. It does have an internal bypass with limited flow, around 3.5 CFS. And they can be configured in a manhole or a vault. These devices have special hydraulic considerations. Filters in general have higher head requirements, operational head requirements than separators. So your site can't be too flat, and they are more sensitive to tailwater conditions. Now, there are certain things that we can do to overcome some of those conditions, the tailwater and the flatness of the site, but it's important to contact us so that we can work through those problems early on. So I prefer one of the things that we like to do is we like to provide 10 inches of drop across the upflow filter inlet and outlet pipe. So what that does, if you look at the inlet here, it places the inlet right at the top of the filter media. So if you just went from the filter, the invert of the inlet pipe over to the modules, those structures, vertical structures, and shown in the manhole, it places the invert right at the top of the media. Flow comes up through the bottom and out of the top of the media. So by placing the pipe at the top of the media, any flow coming into the manhole generates head directly on the media and pushes flow out of the filter bags. That's a condition that we strive for. Another thing to be aware of is, again, the high operational head, or high compared to separators. If you look at the item labeled bypass in this diagram, that elevation 5.46 is the normal water surface elevation inside the device. So when the filter's treating the water quality flow rate, that is where the water surface elevation will be in the filter. So those are the ideals. 9.5, 10-inch drop across the pipes, water surface elevation at 5.46, approximately 2.5 feet above the invert out. Now we can lower those head requirements by adding more filters. We can reduce the drop requirement across the pipes by adding drain down filters. But right now I'm just presenting to you what an ideal layout would look like. Okay, yeah, so this is just reiterating the drop requirements, the operating head. If it's a very flat site, you may not have the head required to make a filter work properly. Yeah, and if you do encounter those conditions, flat site, not enough parent drop, contact us, and we made them work in a lot of fairly flat sites, so there may be something that we can do. And again, there are high. This is one of the products that you really need to take tailwater into consideration. Since these devices require 2.5 feet of operating head, any tailwater on the downstream side is going to reduce the operating head on the filter. So it may require us to increase the number of filters. There may not be a solution, but just want to stress that this is a device that, if you do have a tailwater, it needs careful consideration. And a final thing to consider when designing a upflow filter is drain down time. You may have some storage upstream of the system, and local regs require you to drain it down in 24 to 36 hours. So we can provide a model that you can incorporate into your hydraulic or hydrologic model on site that will help you figure out what the drain down time is of your upstream storage system. Okay, writing a specification. I mentioned the situation where you'll pick up a BMP manual and you'll read 2 or 3 paragraphs and they'll seem to throw in everything in the manual. They'll mention something about a water quality storm, or treating the first inch or the first half inch. And there's half a dozen different ways to define a water quality storm. Or they might say, you got to remove 80% TSS on a net annual basis. So if you get that kind of spec, the BMP manufacturers don't know how to size it, and the engineers aren't sure how to interpret what the basis for sizing is. So, if you get that situation, you could approach us and we can make some recommendations, or we could say, oh yeah, we worked in that area and this is what they've approved in the past. Because of the regulatory environment, many manufacturers have tested their products under various protocols using many different types of particle size distributions. So one thing that a engineer can do, many times they want to evaluate performance of a particular separator. They want to make sure that each vendor's proposing an apples to apples treatment system. So what you can do is you can, and we have them, you can look for these test reports from the the testing that was done for various agencies across the country, and you can usually determine unit equivalency. That clause that says or equal, it'll help you evaluate alternate devices. So writing a specification, try to make it as specific as possible. If you can provide the water quality flow or the method that needs to be used to determine it, that knocks your sizing out. That helps a vendor size their equipment. They know how to size for treatment. And then if you can provide the 10-year or the system design storm, 25-year storm, then they know if their device has the hydraulic capacity or if they have to propose an offline system. Again, this is just a reiteration. Avoid writing a mixed spec if you can. Be clear, concise. Call it the water quality, call it the peak flow, or any other concerns that you may have. If the vendors have to take a tailwater into consideration, that should be in the spec. If they have to limit their head loss, that should be in the spec. Is it okay to have a device online or offline? That's helpful if that's in the spec. And as I alluded to early on in the presentation, we used to see the mixed specs and a lot of specs that were not clear, but as time passes, they're getting better. They're getting much better. But in some of the areas that are still not highly regulated, sizing is very open to interpretation. So if we can avoid that, that's a good thing and results in a well-written spec. Okay, I think that's pretty much covered what I'd like you to be aware of in terms of designing Hydro's products in. Again, the website is there and tech support services is available. We love to get people's calls. Just seems to make projects flow that much better. So I'm open to questions if anybody has any questions.
I can't answer you.
I know. So what? Okay. All right. So as I alluded to earlier in the presentation, there's going to be a post-webinar survey. So please enter that, and you'll have a chance to win an Amazon gift card, $50 gift card. And you should receive your PDH certificates no later than Thursday, December 20th. So that's what I have. Well, thank you for listening in, and hopefully you learned something that was helpful.